Okay, 4.2, our very last section of the class. Okay, now from 4.1, once the scatter diagram and the linear correlation coefficient, that Pearson's R, show that two variables do have a linear relation, we can find a linear equation that describes this relation. So one way to do this is select 2 points from the data that appear to provide a good fit. So for example, let's go to the next slide and see where, here's their scatter plot, and they said, okay, this looks like this would be a good fit. So let's pick 2 points from that line and from the data that we might draw a line through. They chose this one, 2, 5.7, and 6, 1.9. Okay, so you pick 2 points that you think represents a nice line. And from algebra, remember, if you have 2 points, you can find the slope of your line. And once you have a slope and a point, you can find the actual equation of the line. So there's the equation of the line. Okay? Okay, now here's the graph we already showed showing the equation of the line, and they ask us to use the equation to predict y if x equals 3. So they've just taken the equation we found and plugged it in to where, and plug 3 in for x, right, to get 4.75. Okay, so let's go back and look at the actual value when x was 3, 5.2. Okay, 4.75. Okay, maybe not too bad. But that brings up the question, is there a line that fits the data better? Is there a line that fits the data best? Well, that brings up another question. When attempting to determine the best of something, we need a criterion for determining best. For example, suppose we're trying to identify the best domestic car. What do you mean by best? Best gas mileage, best reliability, okay, best what? So, we're going to take the difference between the observed value of y and the predicted value from our equation. That's just a prediction. And that's the error or residual. Okay? So using the line from the last example and the predicted value at x equals 3, we would have the observed value of y, the 5.2, minus the predicted value. So our residual would be 0.45. Okay? The criterion to determine the line that best describes the relation between two variables is going to be based on these residuals. And the most popular technique for making the residuals as small as possible is the method of least squares. Okay, so let's go ahead and look at that. Okay, the least squares regression line is the line that minimizes the sum of the squared errors or residuals. This line minimizes the sum of the squared vertical distance between the observed values of y and those predicted by the line y hat. Okay? We represent this as minimize the sum of the residual squared. So let's say we had our, scatter plot here with our line, and this vertical distance is the residuals. And notice that sum's going to be negative and sum's going to be positive. That's hence where the square comes in, just like when we were finding those standard deviations. Okay? And we want those residuals, those errors, to be as small as possible. Okay? The advantage of this least squares criterion is that it allows for statistical inference on the predicted value and slope. So it leads to these formulas for obtaining it, but in reality we're going to use a calculator. So here's our equation of the least squares regression line. It's given by y hat, and we want to be always be sure to use y hat because that's what reminds us that it's just a predicted value. It's not the actual value of y, it's a predicted value. Notice this is just y equals mx plus b, right? Just a regular line and slope-intercept form, where the slope, we're going to call b sub 1 instead of m, right, can be found by this formula. And the y-intercept, b sub naught, can be found by this formula, where, of course, the x bar and y bar are the sample means, and s sub x and s sub y sample standard deviations, and r is our Pearson's R. So we could use our calculator to enter our data and get the s sub x, right, the standard deviations, the Pearson's R, the means, so we could do that. We could do it. That's what they call doing it by hand. You're really doing all that by calculator anyhow. But we also have something that'll just give us the b sub 1 and b sub naught. Okay? So the least squares regression line always contains the point x bar, y bar, right? It's always going to contain those sample means. All right. So let's do an example. Using the drilling data, which we've seen, and I already have in my calculator. If you don't, you might want to pause and enter this in your list 1, list 2, right? Find the least squares regression line. We're going to do the same thing than when we found Pearson's R. Okay, we're going to go into Stat, over to Calc, and number 4, linear regression, AX plus B. And notice the very first thing that it tells us is y equals ax plus b. It tells us the format it's giving it to us in, and then it gives me the a and the b. So on this one, it tells me that a is 0.011.0116. They're going to want you to round to 4 decimal places probably on all of these. Don't round in the middle of your work though. Wait until the very end if you're doing it, but that's what your calculator has done. If you're doing some of it by hand, right, don't round in the middle. And B is 5.5273. That means that our least squares regression line is y hat, don't forget the hat, is 0.0116x plus 5.5273. Predict the drilling time if drilling starts at 130 feet. So I'm just going to put that in my equation. And we'll see that we get $7.0353. Is the observed drilling time at 130 feet above or below average? Here's the observed time. This is our average time. So it's below average. The observed time was a little below average. Not much, right? 6.97.0. Okay, then it says draw the least squares regression line on the scatter diagram of the data. Okay, so if we're going to do that on our calculator, remember you go in stats and turn your plots on. And then if you do your zoom stat, which I believe is 9, it shows you your scatter diagram. Then that first one where it says y equals, enter that and enter your equation in there. Go back to your zoom stat menu and it will draw that line right on top of your scatter plot for you. Okay, don't forget you can do a trace if you need a couple, if you're doing this, by hand, if you need to draw that for me, you can hit a trace and it will tell you the values of enough points so that you can put it on your paper by hand or wherever you need to draw it. So here it is drawn out for you. Hopefully yours looks like that on your calculator. Okay, the slope of the regression line is 0.0116, which means for each additional foot of depth we start drilling, the time to drill 5 feet increases by this many minutes on average. Now notice this on average. That's going to be really important for us. Okay, interpreting slope for least squares regression line has a little bit of a twist. Statistical models, such as this one, are probabilistic, right? Probabilistic. That means that any predictions or interpretations made as a result of the model are based on uncertainty, probabilities, likelihoods. Okay? Therefore, when we interpret the slope of a least squares regression equation, we don't want to imply there's 100% certainty behind the interpretation. So usually on the end you just add on average. You might include something like the expected time to drill 5 feet increases by this many minutes, right? But usually just adding on average, but that's important. Okay, another little twist. The Y-intercept of the regression line for our example is 5.5273. To interpret the Y-intercept, though, we first have to ask ourselves 2 questions. Is 0 a reasonable value for the explanatory variable? And do any observations near 0 exist in the data? Okay, so let's think about our example first. A value of 0 is reasonable for the drilling data. That would just indicate that drilling begins at the surface of Earth, right? And the smallest observation is 35, which is reasonably close to 0. If you're talking about drilling miles down into the Earth, 35 feet is reasonably close to 0. So the interpretation of the Y-intercept is reasonable, which would be the time to drill 5 feet when we begin drilling at the surface of the Earth is 5.5273 minutes. Okay? If the answer to either of these questions is no, though, you cannot interpret the Y-intercept, right? Do not interpret the Y-intercept. Okay. Be careful. If the least squares regression line is used to make prediction based on values of the explanatory variable that are much larger or much smaller than the observed values, we say that the researcher is working outside the scope of the model. So not only for that Y-intercept question, but that's what this would be related to. If it's not, if 0 is not an observed value, you'd be outside the scope of the model anyhow, or near 0. Never use a least squared regression line to make predictions outside the scope of the model, because we cannot be sure the linear relation continues to exist outside the scope of the model. Okay, let's look at one more example. Weight of car versus miles per gallon. An engineer wants to determine how the weight of a car, X, affects the gas mileage, Y. Now notice they've told us which one's X and Y. That's because in this one, he could want to determine how the weight of how the gas mileage is affected by the weight of a car, right? Sometimes we have to determine which one's the explanatory and response, but sometimes it just depends on what the researcher's interested in. So they've given us the X and Y this time. The following data represent the weights of various domestic cars and their miles per gallon in the city for the 2015 model year. Okay, find the least squares regression line. Now, I've already entered this information just to save time, so if you need to pause the video and enter this either in your L1 or L2, I've got it in L3 and L4 just because I had the other in L1 and L2, but pause and enter the information. Okay, I already have, so I'm going to go into Stat, okay, over to Calc, and hit 4, but this time, since I'm using information in L3, it'll default to use L1 and L2, but I'm going to tell it L3 and L4. Okay, and so it gives me my A and my B, so I can just get my Y hat, negative 0.0047, that's rounded to 4 decimal places, X plus 37.3569. Okay, so this says interpret the slope and y-intercept if appropriate. All right, so let's think about the slope first and what this means. First of all, X is the weight of the car, Y is the gas mileage. So this is affecting the weight of the car, right? So for every pound added to the car, the gas mileage is decreased by 0.0047 miles per gallon, right? Every pound added to the car, the gas mileage would be decreased by this, by 0.0047 miles per gallon. Now, what about the y-intercept? Does it make sense for the weight of the car to be 0? And do I have any values close to 0? No, it doesn't make sense to interpret a y-intercept in this case. Okay, a Cadillac CTS weighs 3,649 pounds and gets 20 miles per gallon. Is the miles per gallon of a CTS below, above, or below average? So let's get a prediction. All right, this car weighs 3,649. Okay, and enter it in our calculator. And I get 20.2066. Okay. So is the miles per gallon of a CTS above or below average for cars of this weight? Okay, the average is 20.2 for a car of this weight, and this one gets 20. So it's below average for a car of that weight. Would it be reasonable to use the least squares regression line to predict the miles per gallon of a Toyota Prius, a hybrid gas and electric car? Oh, no, I'd say no. Why or why not? Because we're talking about miles per gallon, and being hybrid electric, that's what's going to greatly determine the miles per gallon, not the weight of the car, right? You've got a huge other factor on miles per gallon for that kind of car. Okay, let me know if you have any questions. Good luck. It was nice working with you guys.